Hello, welcome to this problem solving session. So we'll be solving a problem today. I've already written out the solution, but I'll walk through it just to make things very easy to understand and make things clear as well too. So a 40 kilogram platform is attached to the end B. This is B here, or a 50 kilogram wooden beam AB, which is supported by a pin at A and a slender rod BC. With 12 kilonewton ultimate load PU, right? Using the load and resistance factor design method with a resistance factor that's phi equals to 0.9 and load factor gamma d 1 point, that's the dead load factor 1.25 and the live load factor 1.6. Determine the largest load that can be placed safely on the platform. What is the corresponding conventional factor of safety for rod BC? Now, for solving these problems, typically you can use either the conventional factor of safety method or the load and resistance factor design method. So the load and factor resistance method, that allows designers to distinguish between uncertainties associated with the live load. With live load here, that means the active or time varying load that is supported by the structure, or the dead load, which in this case here is the self weight of the structure, which of course both of them contributes to the total load, right? Now, in solving this problem, first of all, it says for us to find, or use this method, where is that? The load and resistance method. Of course, for problems like this, we start with the free body diagram because we want to demystify all these forces, get to know the components. Now, in drawing this here, let's concern ourselves with AB. Now, for AB here, there's a pin here, so we have two forces here, Y and X. Now, for this AB, that's the wooden platform or beam, right? There's a force acting at the center, which is W2 here. This weight due to this W1. Now, this rod here, slender rod BC. Of course, you see this is acting downward. There's another force acting here. Let's call that force P to keep this in equilibrium. So we have a force. Now that P is at an angle, right? It's safe to call that 45 because here we have 90 degrees and here 45. It's safe to call that. Now for this problem, we can resolve P into two components, Px, Py here, right? Now for the problem, we can see problem is beginning to take shape in the sense that we can see our vertical and horizontal forces. Of course, you can easily sum the forces in the x direction to be equal to 0, forces in the y direction to be equal to 0, but you cannot sum the force if it's inclined at an angle. You have to resolve it. Now in resolving this, we don't have an angle, but again, from what we've just established by, if you look at this, right angle, you can see that we have, we can use this 3, 4, 5 triangle, like a Pythagorean theorem, or triple, right? So if we use similarity, similarity here, we look at this, the first P is here at an angle, take that to be here, this is P, right? First can resolve this to the Y component and the X, and that's P here, we take that to be the largest angle, largest side of the triangle. So we have that as 5. So we can say Py corresponds to 3 and Px equals to 4. In that light, we come up with this expression 5 over 3, that's 5. Here we have 5. Then we have P here. Then 3 in the vertical part, Py here. So we come up with this expression. Now with this expression, we are just simply expressing Py in terms of 3P, to become 3P over 5. We're expressing Py in terms of P, right? Now, the idea behind that is we can easily equate, if we want, that's if we decide to, we can easily equate all the vertical forces, 1, 2, 3, with this one, because we now have a corresponding path. Okay, now in solving problems like this, for us to get real, we get a value instead of just numbers, or just letters actually. We take moment about point, the place where we typically have the the highest number of unknown forces. Yeah, yeah, we have two. Yeah, we don't know any of these forces. We know this down, though we don't know this. I mean, we don't know this by extension. We don't know this too, right? But then we have this as an expression here. So we take moments about point A, about point A here. Now, for this one, we take the convention anti-clockwise is positive. So the W2 and W1 are acting downwards, negative, right? So we assume if you force apply, they tend to rotate this way. However, this force tends to go this other way. When we pull this way, right? So that's why we say negative, and of course W2, which is due to the weight of this beam, is acting at the center. So W2 at the center, which is 1.2, half of this, half of 2.4 divided by 2, right? Minus W1, which is at the very end, so multiply by 2.4, plus, now we have here Py. Py is 3P5, which is here. From also is at the end of the beam, so that's 2.4 is equal to 0. So that's the force, right? PD. That's the dead load itself. So the dead load itself now, it's, if you equate this, you get 5 over 3 W1 plus 5 over 6 W2. That's algebra, so I don't need to explain. I don't waste time explaining how we came from here to this. You simply take, if you take this W2 and this all to the next other side, or you take this to the other side, then it cancels out, then you come up with this expression, which is PD, the dead load. Now for the dead load, dead load is the weight or the self-weight of the structure contributing to the total weight, right? But for the live load, that's the active or time-varying load, right? Now, this beam will always have a weight, whether you apply force to it or not, right? But for this one, you can always change it, right? It can change based on what you decide to give that to it. So now, for the dead load, W1 first, the weight due to this point, right? W1, 40 kg or 40 kilogram. 40 kilogram multiplied by 9.8 to convert that to Newton. For W2, the same, 50 kilogram, which is to the center here, multiplied by 9.8 to 490.5 Newton. So then we now have W1 and W2. We put these expressions into the dead load expression we had previously gotten. So that simplifies this and gives us the value for PD, which is this, which is 1.0628 times 10 to the power 3 Newton. Now for the live load, W2, for live load, we don't consider the weight of the beam, right? So this W2 becomes 0, but then we consider this, right? W1. Now we know that W1 as weight equals to mg, the mass times the acceleration due to gravity, right? At this point, W2 here is 0, so that cancels this part of the expression, cancels that out. Now for P, so okay, yeah. So if you use this same expression here, because this cancels out, at this point here, you make W, you change this to mg and make m the subject of the formula, which is this, and make m the subject of the formula, which is simply multiplying PL by 3 and dividing by 5g, which gives us this here. Now, when you want to use this method, the load at which the structure ceases to be useful, which is ultimate load, right? PU, typically you can determine it through this expression. So this is the proposed design criteria, basically. And for this one, we have, which is simply by, it's like finding the contribution of the dead load and the live load to the total load. And of course, this to ultimate load, you need a resistance factor. You can't, safely, you don't use all of this ultimate load, because then that's pretty risky. So you multiply the load factors, which is gamma D, dead load, that's for the dead load, the ultimate load, which is gamma L, by dead load on the live load. So for this problem, we already have this expression, right? So from the problem, if you look at the problem, we're given some constants already. For these constants, we're given the resistance factor 0.9, load factors 1.25, the dead load factor and the live load factor 1.6. So if you put all of this into this expression we already have, we can use that to simplify this expression, right? We can use this to simplify this expression. Now, we make PL the subject of the formula, making that you simply have this, you bring this one over to this part here, then you divide by the load factor, gamma L. Now for this, we're just simply substituting 0.9, the ultimate load, because in the problem it was given as 12 kilonewton, which is here, ultimate load. That's the maximum load that rod can handle. Of course, it's in kilonewton. You always want to use your units in newton, or keep things consistent generally, right? And here 1.25, and here PD. So this is from, let's see, it's here. Right? It's PD is here. We had calculated the dead load there. So we're using that here, divided by 1.6, which is this one. So here we get the live load, which is 5.2 times 10 raised to the power 3. So then to calculate the allowable load, meaning this is, once you know the mass, this is the maximum mass you can add on this side. This W equals to mg, sorry. This W equals to mg. This is the maximum load you can add in this place for this structure to remain, safe, for it to remain safe or not to collapse or be destroyed. If you go beyond that m, this fails. Right, so that's basically what we are trying to calculate here. So here, remember, we've gotten what PL is, and also we have computed PL, it has a live load based on this expression, which in turn gives us something for the mass. Now that we know what PL is, we can simply put this PL into this, then get 3/5 times PL divided by acceleration due to gravity G. So the maximum load that structure can withstand is 362 kilogram. Anything beyond that, then it collapses. Now for the factor of, now that's exactly what the question wants us to do. Determine the largest load, right? Now the other part, which is also an interesting part to the problem, typically instead of calculating the contribution of both the dead load and the live load, here what you are typically taught or shown is what is the corresponding conventional factor of safety for the rod BC. For this one, typically you already know you want the ultimate load that it can take, right? The ultimate load compared to the total load. That's the idea. So the fact, yeah, that's okay. I've already written this down. The ultimate load compared to the total load, right? Now for this ultimate load here, PU, if you look at the problem, it says with the 12, this ultimate load, that rod, so that's the maximum it can take. I mean, that's, yeah, by slender rod, the maximum ultimate load of this, which is that here is giving us this, right? Now to find this total load, is the dead load plus the live load, right? That's what will give us this P. Now for this dead load, I think we've computed that PD here, right? And from this one, we came about this expression when we are taking moments about the parts, which is here. So now for the live load here, for the live load, we are simply, I mean, which is this, right? We simply made use this formula, our design formula. We made PL the subject of the formula, and that's how we came up about this value here. So the total load would be the load due to the dead loading, or due to dead weight or load, and live load. That's how we get a total, right? Of course, this is only a fraction of this, because it says 12 maximum. anything, the closer you are to 12, I mean, the more risky it is, right? So then the conventional factor of safety is simply the ultimate load divided by the total load. It gives us 1.718. I hope this helps. Cheers.